What's up, everybody, and welcome to episode 2 or lecture number 2 in your Unit 8 on chemical bonds. In this lecture, we are going to talk about covalent bonds and the two types of covalent bonds and a way of determining bond type more than just looking at the types of elements in bonds. But enough with that, let's get into the notes. First thing I'm going to talk about today is something called electronegativity. And electronegativity, abbreviated EN for short, alright, has to do with the tendency of an atom to attract electrons when it is bonded. Alright, so this is very similar to electron affinity, where that's how much an atom attracts an outside of an electron. It has that attraction of electrons again, and it's similar to ionization energy, where how much the nucleus is holding on to an atom's own electrons. And what we see that the most reactive metals, which have very low electron affinities and very low ionization energies, also tend to have low electronegativities, whereas nonmetals have high electronegativities. And we can use these electronegativities and subtract them in what is known as an EN difference to determine the bond type. And so we have some numbers that are set based on these EN differences that determine whether we have something being ionic, covalent. And we can see that there are two types of covalent bonds, both polar covalent and non-polar covalent bonds. And the greater the difference, the more ionic the bond. And we'll talk about the polar and non-polar bonds in a second. But before we get into polar and nonpolar bonds, we need to kind of talk about covalent compounds as a whole. And one of the nifty things about them is covalent compounds are also called molecules. And those two terms, covalent compound and molecule, are used interchangeably quite a bit. So in a covalent compound, in a molecule, electrons are shared between atoms, which is different than what we see happening in an ionic compound where the electrons are transferred. There's a moderate to low electronegativity difference. It's less than 1.67, and we'll see actual numbers in a little bit. And typically, if we're just looking at elements making up a bond, we're looking for things that are nonmetals to nonmetals, maybe nonmetals to metalloids, something like that. Over here, we have a couple of different examples. We got phosphorus trichloride, which is a phosphorus, a nonmetal, 3 chlorines. There are 3 different bonds there between the phosphorus and the chlorine at 3 spots. This picture shows it best with the inflated balls. We have water, and we have carbon dioxide. And all 3 of these, we are dealing with nonmetals, and we are dealing with substances that, generally speaking, have low melting points, are poor or inept conductors of electricity. They are more insulators, and they tend to be fairly brittle as opposed to strong, hard, and malleable and ductile that we talked about in the last lecture when we talked about ionic and metallic things. So what is the difference between these two types of covalent bonds? Well, first, the nonpolar covalent bond is a bond where the EN difference is very low or 0. Typically, it is less than 0.4. The electrons are shared equally, and if we're just trying to look at something and trying to tell just based on the type of elements, we pretty much assume any element bonded to itself or a carbon to hydrogen bond is nonpolar. And that's if we don't have electronegativity values around, we're just taking a quick look by inspection of looking at the two elements. On the other hand, a polar covalent bond has more of a moderate EN difference. It's between that 0.4 cutoff for nonpolar covalent and that 1.67 cutoff for ionic. And if we're taking a look at these are bonds that are all the other covalent bonds that are not elements bonded to themselves or carbon to hydrogen. And again, this is just if we're looking, not if we're actually using electronegativity difference. This is just kind of inspecting the two atoms and predicting based on what type of atoms we have. If we have EN values available, it is better to subtract the ENs of the atoms in the bond to find out what type the bond is that way. In this case, the electrons are not shared 50-50. There's not equal sharing. This is the situation where, the atoms are not playing nice in the sandbox. They're kind of sharing their Tonka trucks in the sandbox, but, the one kid's playing with the Tonka truck a little bit more than the other kid. And so it's not a nice equal sharing. All right? It's not the kid stealing somebody else's Tonka truck and running home. That's more ionic, where you just got one thing taking it from the other. This is more of a sharing situation. It's just not a nice equal sharing situation. What we got here is we're going to look at a pair of elements, and we are going to determine whether we have an ionic or covalent bond. And I'm even going to go a little further and say whether it's polar or nonpolar covalent, just based on the atom type. So to start off, we have got aluminum and silicon. Aluminum is a metal, and silicon is a nonmetal, or a metalloid, sorry. And so we have our metal and our metalloid here, and when we have a metal and a metalloid, or a metal and a nonmetal, we would predict it would probably be ionic. We would say ionic there. In our second example, barium again is also a metal. It's the bottom of group 2. And we have oxygen, which is definitely a nonmetal at the top of group 16. Metal and nonmetal is ionic. Remember, the presence of a metal generally leads us to thinking something is ionic. In the third one, we have carbon bonded to hydrogen, and these are both nonmetals, but I pointed out which elements they were because this is the special one right here that you really need to know. Is carbon and hydrogen is considered nonpolar covalent. It is considered an equal sharing of electrons, and that's kind of a special one when we're looking at just elements like this. Number 4, we have lithium. Again, that's a metal. It's element number 3, right below hydrogen. And sulfur, which is right below oxygen, making it a nonmetal. And again, we have an ionic compound that we see here. As we mosey on to number 5, we got calcium. Calcium, of course, is a metal. Calcium is a group 2, an alkaline earth metal. Phosphorus is below nitrogen in group 15. It is a nonmetal, so again we have an ionic compound. Boron and fluorine. Boron is the top of element 13. Boron and fluorine are both nonmetals, and they are two different nonmetals. I don't know what happened up there on number 5, but I'm still kind of getting to learn the program, so we'll keep it going. So we got two different nonmetals. That would mean we not only have covalent, but we have a polar covalent bond. Carbon and chlorine, again, two different nonmetals. All right, remember the only time we have to know that two different nonmetals are nonpolar is when it's carbon and hydrogen together. So here, carbon and chlorine are two different nonmetals. We're going to call this one polar covalent as well. I guess I went a little fast there. Didn't catch up with myself. On number 8, we have fluorine, the top element in the halogens, group 17, and we have sulfur, who is right below oxygen in group 16. They are two different nonmetals yet again. Those two different nonmetals are not carbon and hydrogen, because they are fluorine and sulfur, so this would be considered a polar covalent bond. And finally, at the bottom, we have bromine, down there in the middle of the table for the halogens. Group 17 is a nonmetal. And we have Rb, which is rubidium, which is, halfway down the table of the alkali metals in group 1. So we have an ionic bond there. And that's how we would take a look at these based on atomic or atom type. What we're going to do here is we're going to do the same thing, but with En difference using this chart of electronegativities. It's a little different than the one in your book, but it will work pretty well. And we're going to do the same 9 compounds. So we're going to start off with aluminum and silicon again. And the first element we're going to pull out of aluminum and silicon is, of course, going to be silicon. Silicon has electronegativity of 1.8. Aluminum, its next door neighbor, has an electronegativity of 1.5. So we're simply going to take 1.8, subtract 1.5. We don't want negative numbers, so always put the larger one first, or take an absolute value. We get 0.3, which is less than 0.4, so this is actually more like a non-polar bond, even though we probably classified it as ionic on the last page because of the metal. In the second one, we have barium and oxygen. Oxygen's right here, nice 3.5 as its electronegativity. 3.4, 3.5. I might have used a different chart when I wrote this. And the other one was barium, which is right here at 0.9. In either case, if I subtract the two, I get about 2.5 or 2.6, which is well over that 1.67 area that we talked about, so this is definitely an ionic compound. Carbon and hydrogen we said was nonpolar covalent. Let's see what we get here when we start actually looking at the numbers. We're going to start right here with carbon. No, we're going to start with hydrogen. Hydrogen is 2.1. It is the smaller of the two numbers. 2.2 I have there. Here we got carbon at 2.5, and we get 0.3, which is also nonpolar covalent. For the next one, we have sulfur. Sulfur's over here at also 2.5. Like what you would expect, 2.6 based on the chart. I'm using the chart from your book instead of this one, and I'm rounding to 1 decimal. Lithium is 1.0. 2.6 minus 1.0 gives us 1.6. That is in that polar covalent range. If I used the 2.5, it even puts it more solidly in that polar covalent range. Phosphorus is at about 2.1, 2.2. While calcium is at 1.0, I get 1.2, again solidly in that polar covalent range, not the ionic that we would have predicted because of the metal calcium that is in there. Boron and fluorine. Fluorine is 4.0. Boron, right over here, is around 2.0. And 4 minus 2, last I checked, is 2, making this an ionic bond, even though they're both nonmetals. So it kind of works both ways. Remember, that other one's just like for a quick check. Carbon and chlorine. Chlorine we have as at 3.2. Carbon we have at 2.5. So this leads to about 0.7, which is in that polar covalent range. If we went with the 3.0 number, would be at 0.5, still that polar covalent range. Number 8, fluorine and sulfur. Fluorine we did earlier, it's right here, it's at 4.0. Whereas sulfur, kind of diagonal to it, is at 2.5. 4.0 minus 2.5 is 1.5, which gives us a polar covalent bond as well. And our final one, bromine and rubidium. Bromine's over here at 2.8. Rubidium in that first family of alkali metals at 0.8. That subtracts to give us 2.0, which also is ionic. So you can see using electronegativities does make a difference. The chart we use also makes a difference. So, sorry about the little confusion with the numbers being a little off. If you look at the chart that's in your book, you will kind of see how I got some of my numbers that might be slightly different. But other than that, you just take the numbers and subtract them, and then you have a better idea of what kind of bond you really have. Although, just looking metal, non-metal, metalloid, it works pretty well and is a lot quicker than having to look up a chart and doing some subtraction. So either way can work. Any kind of questions you would ever get would specifically tell you either to just look at the elements, or if you need electronegativities, they would be provided for you. Thank you, and stay safe and healthy, everyone.